Hello everyone, welcome back to Calorimetry and Energy Flow. This is part 4. This is where we are going to begin quantifying the amount of energy that is transferred during processes. Now, these processes for the energy transfer, they can be chemical, they can be physical, they can be as simple as a hot thing up against a cold thing, or as complex as a reaction that is creating heat. So we work with this. We often are looking at systems where we can't actually measure the system. So if an example of this is if we have a beaker filled with water and we add in a type of salt, let's do NH4Cl, ammonium chloride, and we add that salt into the water. The salt is going to undergo dissolution. NH4Cl is going to get solvated with the water, breaking up into NH4 plus aqueous plus Cl minus aqueous. This process of dissolution is either endothermic or exothermic. It's going to either require energy or give off energy, depending upon the salt that we are going to use. And I don't exactly remember what it is for ammonium chloride, but the point is here, we cannot stick our little molecular level probe to be able to measure the NH4Cl directly, because we'd have to have the little probe sitting on every single molecule of ammonium chloride to be able to see what is happening with each one of those and be able to measure the energy from that. We can't really do that. But what we can do is we can stick a thermometer into the water and we can watch the temperature of the water change based upon what's happening with the ammonium chloride. And so this is an example of when we can't measure the system. When we can't measure the system, we often try to measure the surroundings instead. And we use the relationship that energy is conserved. And so if the system is giving off energy, that energy has to be absorbed by the surroundings. Or vice versa, if the system is requiring energy, it's absorbing energy, that energy must be provided or given to by the surroundings. And so the heat from the system is going to be equal to the opposite value, the opposite magnitude of the heat of the surroundings. So how do we use this? So let's do an example. We have a 31.1 gram wafer of pure gold, initially at 69.3 degrees C, and we dunk it into 64.2 grams of water at 27.8 degrees C in an insulated container. And we want to know what the final temperature of both substances are at thermal equilibrium. Okay, so what's going on here is we have a container. We're going to add water and we're going to put in gold into our container. And our gold is going to be hot. And our water is going to be colder. And so this out here this is water and it's cold. And so the heat is going to flow from the hot thing, from the hot gold, out into the colder water. And eventually, the temperature of the water and the gold will be equal to each other. So heat will flow until the final temperature of the gold is equal to the final temperature of the water. This is thermal equilibrium. Okay, so let's figure out what we know. In this problem, the gold is going to be our system, and the beaker with water is going to be the surroundings. The gold has an initial temperature of 69.3 degrees Celsius and a mass of 31.1 grams. The water has an initial temperature of 27.8 degrees Celsius and a mass of 64.2 grams. And so with this, we know that the heat is going from the gold to the water. So that means that heat is leaving the system. So the Q of the system is going to be less than 0. And heat is added to the surroundings. So the Q of the surroundings is going to be greater than 0. And so we can write this as negative Q of the system is equal to the positive Q of the surroundings. Now, we also know that Q is equal to the mass times the specific heat times the change in temperature. So what we are going to do is we're going to set up, remember on the last slide we said that Q is equal to MC delta T, and that negative Q of the system is equal to positive Q of the surroundings. And so what I'm going to do is I'm going to combine these two equations. And so I have this side of my equation for the gold, and this side of the equation is for the water. And so thermal equilibrium is when the final temperatures are equal to each other. And so what I can do is I can break apart this delta T as TF minus T initial, but I make my initial temperatures specific for the species that I'm looking at, whereas TF is going to be the same for both systems because we reach thermal equilibrium. Okay, so now let's try to plug in numbers and solve this problem. So what we have is negative mass of the gold times the specific heat of the gold times T final minus T initial of the gold is equal to the mass of the water times the specific heat of the water times the final temperature minus the initial temperature of the water. And this is the same equation that was on the previous page. So now I'm going to just plug in numbers. And these are from the problem. So I have 31.1 grams of gold. The specific heat of gold is 0.128 joules per gram degree Celsius. The final temperature is what I'm looking for, and gold started at 69.3 degrees Celsius. And I'm going to I'm going to switch colors for the other side just so that I know which one is water and which one is gold. My water, there were 64.2 grams of water. The specific heat of water is 4.18 joules per gram degree Celsius. We are looking for TF, and the initial temperature of water is 27.8 degrees Celsius. So you'll notice that I forgot to put the specific heat of water in this problem. That is common in these types of problems. To find your specific heat, there is a table on page 259. It is table 6.4 in your textbook that has a table of specific heat values. So if you are working problems and need a specific heat, this is where to go. Okay, so to solve this problem, I'm going to do some algebra. And so I get negative 3.981 joules per gram degree Celsius times TF minus 69.3 degrees C is equal to 268.4 joules. Whoops, I made a mistake on my units over here. I gotta get rid of that because the grams canceled out as I worked the problem. Joules per degree C times TF minus 27.8 degrees C. Rearrange things and I get negative 3.981 joules per degree C times TF plus 275.9 joules is equal to 268.4 joules per degree C times T final minus 7461 joules. And so I get 272.4 joules per degree Celsius times TF is equal to 7737 joules. And I find that the final temperature is 28.4 degrees Celsius. So now we have to make sure this makes sense. Remember that the gold started at 69.3 and the water degree C, and the water started at 27.8 degrees C. And we said that we had our gold and the heat was flowing out into the water. So we would expect the temperature of the water to increase and the temperature of the gold to decrease. And based upon our final temperature, this is the case. And so this is your sanity check for these types of problems. Okay, so this is what we call calorimetry. It's really measuring the heat flow from a system to the surroundings. And because of this, with this final what we can do is we can stick a thermometer into this water and we can measure this change in temperature of the water experimentally and find things out about our gold. And so this makes us it makes these experiments a lot easier. Okay, so stay tuned. We are going to keep working through problems involving heat and energy flow, and keep up the good work.